Welcome to our second lectures on interline power quality conditioners. So, on AC flexible transmission system, we shall continue with this actually the operating principle of the IPFC. So, what we were discussed in our previous class that in general at a selected operating point the converter has to exchange both reactive and the real power with line 1. However, converter can internally generate the reactive power, that is all by managing the angle between the voltage and current, and thus it must be supplied with the real power exchange capabilities and it should exchange the real power. The real power demand remains constant while internally generated reactive power changes. So, we can move to a point of different Q and while the real power demand change. The constant operating point of the converter is shifted along the selected line of the voltage compensated line, which we have seen earlier. These are all dotted chords. Dotted chord changes from diameter to the upper hand, the lower half. So, since the length of the chord decreases, so amount of the compensation increases in when actually you have a low degree of the real power compensation. As you go up, reactive power flow also will be actually reduced because of the size of the chord will be reduced. Moving to the operating point, one point to the another operating point of the line to another change of the real power demand of the converter and shifts the resulting receiving end real and the reactive power in parallel line in P1 as well as the Q1 of the control line. So, that is what we have understood. So, you got a chord, this is the line where there is no compensation, you go above. So, you have to give the little real power or you have to absorb little real power, and in this line you have a actually compensation of the reactive power which can be manipulated by exchange of the angle, because essentially what you are changing basically amount of V1Q and ultimately you can operate anywhere, but as you increasing, so your compensation decreases. So, in order to satisfy the active power demand of converter 1 operated along the selected voltage compensations line, any line here or here, even here where actually there is no compensation of the real power, converter 2 must be operated along a complementary voltage compensation line. So, as to precisely supply this demand real power from line 2 via common DC link converter 1. The operations of the 2 converter IPFC scheme is illustrated with the help of the complementary voltage compensation of Q1 versus P1 of the control line, which we will see in the next slide. For this illustrations, actually let us take some examples. 3 particular operating point of the converter 1 marked A1, B1 and C1 located at the arbitrary selected voltage compensation line. So, we will see that in the next slide. So, we have to mark A1, B1, C1, these are the 3 operating point of IPFC converter 1 of IPFC. The corresponding Q1R, P1R of the line of Q1R and PR plane with the specific reactive and the real power values obtained in the 3 operating point, and it has been shown in coming figure. So, this one is a A1, and so see that here this line corresponds to the constant PQ line, As said earlier, when there is no exchange of the real power, this is the line, and ultimately this is the rho, and this will be a different chord of where value of the P1Q is constant, and this is the I1, and this value will be actually Vx1, and this angle is delta 1 by 2. So, this point, let us assume at this point A is basically A1, and this is the point. Similarly, the power corresponding to this line is P1 equal to 0. Similarly, this line corresponding to this, actually if you go by this line, exchange of the reactive power in between this line is 0. So, Q1 is 0, and you are operating the same operating condition, that delta equal to 30 degree. So, you are here, and you are increasing delta, then you will be shifting like this. So, this is the explanation of it, and this is the case of delta equal to 0. And what happen if you wish to change, if you wish to actually move along this? So, amount of the P1 is a constant, P12 is a constant. If you want to move in this way, so amount of the PQ will be constant, amount of the Q1 is constant, and this is the example where it is a case, it is above. So, it is basically the absorbing the real power. This is the operating reason for A1. Similarly, we can find that B1. Please note that what is the change in A1? A1 is actually here, and we shall make it this point as B1. So, this point becomes B1. It is same here, voltage B1 is PQ. Ultimately, it was here you have given a voltage V1 PQ, so that this operating point shifted to B1, and that's what happened. So, ultimately you were here, from here you have shifted there. Again, in the same case, this is actually constant PQ line, here power exchange is 0. So, ultimately you have exchanged some amount of the real power, some amount of the imaginary power. Please see that actually this is the component where Vp1 is 0, you require to inject. So, ultimately you have injected V1Q in this line, and also you have to inject some amount of the Vp1, so that it can shift it there. So, for this reason, what happened, this point which was originally uncompensated line was operating here, it has been shifted with the voltage of the PQ, and see that what is the amount of the actually real power been exchanged between these 2 points, and ultimately same way this is the line delta. So, next let us consider that C, again same thing. So, you were here initially, this was B essentially. Now, you have shifted to this point. So, essentially your original point of location was this at delta equal to 30 degree uncompensated line. Now, you have injected this voltage V1 PQ, and you have moved to this point. So, ultimately what happened? So, this corresponding this line becomes C, and this line become a 1, and same for the other cases as is been explained with the case of the A1 and B1. Let us see that in 3 cases what are the exchange of the real power. That is actually that is what through discuss, because it cannot, converter cannot generate real power, it has to actually, it has to take a loan from the another converter or the supply to the other converter. Thus, what we can from this discussion, what we can actually take aways are the phasor diagram of the corresponding Q to R and P to R plane with complementary voltage compensation of Q to R and P to R versus control line as shown in system 2 at the left and at the right hand of the figure shown below. The operating point, that is actually A1 which we have shown, is selected so that the injected voltage phasor V1q is perpendicular to the resultant voltage V1x across the transmission line with an impedance, receiving an impedance is actually has been named as XR. As a result, the line current of phasor I1 is in phase with the V1 PQ, and thus converter 1 provides strictly the real power. Please note that, to provide strictly the real power compensation to reduce the reactive power line of Q1 to 0. So, this is the way of operating. Please go back to the 1, then only you will understand. This is the case. So, ultimately it will inject the voltage in this way. So, what happened here, this is the line corresponds to actually 0 value of the PQ, and ultimately the point will be shifted here. It is evident that the converter 2 can satisfy the real power demand of converter 1 by operating at the complementary point of the 2A, which increases the reactive power of line 2 as shown in the case of A. So, this is basically the A1 and this is basically the A2. So, ultimately what happened, the reactive power of the second line will get increased to compensate this line. So, what happened here, you see that actually this is the line where no exchange of the real power takes place, thus actually V2P in phase is 0, and this is the line corresponds to V2Q, as this line is 2A. You have shifted this line here. Previously, please recall that where it was A1. So, here it was essentially A1, you have shifted to, so you have shifted to Calcutta to Melbourne, something like that. So, this is your 2.2A. Essentially, what you do, you have a constant P1Q and you have operated at this point. So, ultimately, so this angle become unchanged. Similarly, you can see that this point is basically A2 and this is the operation of the converter 2, what we have seen there in converter 1. So, thus it is written as A1. Same thing, just you are actually it has been since you are operating here. So, it should be operating this operating point. So, it should be actually within this chord. So, similarly, the point B will be the same thing, it will be shifted here. So, where was the point B1? So, it was here, so it has been shifted here. So, this is the line of point B2. So, other conditions what we have explained, it is absolutely same, the same operation as just reverse. So, ultimately it has to take power. So, it has to inject this value of the VPQ, and essentially in this point you can see that you have to inject little bit of positive real power, here you have to absorb the real power. Similarly, you can operate within these 2 points. So, this was a A2 for the operating condition for line A1 and this one is your 2B. So, similarly, this is a case of the line where real power exchange, imaginary power exchange is 0 and this is actually the real power exchange is 0. Here it will go to the according to the magnitude. Thus, from the discussion similarly it will be for the 2C. From these figures, the important observation can be made with the range of the capacitive compensation in particularly independent of the real power compensation provided. So, it can have a separate independent power flow of reactive and the real power. By contrast, the range of the attainable inductive compensation decreases with the exchange of the increase of the real power with the compensation line. So, this is one of the disadvantage. So, it can compensate capacitive bar quite well, but it will not have, since the length of the cord decreases, since you have actually exchanging the real power. So, inductive capability will be reduced in case of, but generally load are inductive. So, for this is an IPFC actually put it to the very dominance position in our fax devices. For this reason, the reason for is that with the increasing inductive compensation, the line current decreases. So, we have assumed that line current actually remains constant, and the converter having a limited voltage rating. So, you cannot increase the value of the voltage. So, it has to have a device actually compelled you to restrict yourself to a particular voltage rating, and is unable to provide the required total output VA in the available line current. So, it is a very good capacitive bar compensator. The required control range for the reactive and the reactive line power is usually appreciably smaller than the required for the real power flow control. Generally, it has to manage more and more real power than the reactive power. Therefore, theoretically the circular region which we have shown that P and Q are balanced, but it is not so. So, basically we have to inflate it the diameter along the P, thus it becomes ellipse. Circular region in practice can be limited to a appropriate upper and the lower boundary of QR and the PR line control to considerably greater degree that has been illustrated. So, another consideration is that series compensation in practical applications are usually employed to increase rather decrease the transmitted power. Most of the cases, or rather except the fault, we require to increase the transmitted power. The relationship established for the two converter of IPFC are summarized in the figure below, next slide, where two phasor diagram together with corresponding sending and reactive power, that is QR versus PR plot characterizing the two line power system will be shown. So, this is the case of where both 1 and 2 had been merged. So, this is essentially the voltage compensation line. So, this is the angle rho 1 and this is the line corresponds to the actually 0 injection of the VQ1. So, there is no reactive power capability. Similarly, this diameter corresponds to the 0 injection of the VP1 and you are operating here, that is Vs1 and delta 1, and similarly this is operating point here, and this is actually essentially what it has been shown. This much is the inductive region of compensations, and this huge area is the capacitive region of compensation. So, this is the drawn line. So, here this line actually does not compensate, this is the operation of the unity power factor. So, you take this operating point, let us assume that you are operating here, and you can see that how it will be changing. Similarly, this region reactive compensation line control, where actually you have no exchange of the real power P12 equal to 0, and here this is actually the PQ line of P1 PR1, and this is a way of phasor diagram of converter 1. So, thus it will be actually the something like mirror image of converter 2. So, see that, so it will change. So, operating point will be the same. So, it will be actually V2Q. Now, this will be the delta, and this is the, these chords are the, ultimately it will make a parallelepiped. So, basically you will have a cylinder kind of thing, and these lines essentially are the voltage line compensations. So, this line corresponds to similarly the no exchange of the real power between two converter, B2Q is 0, and this line corresponds to again the no exchange of the real power, B2P is 0. So, ultimately you are operating here, and these are the line PQ, and where this line corresponds to no exchange of the real power, and this is the region of the inductive region, and this is the region of the conducting region, and this value is corresponds to, this is a delta line, how this actually circle of influence will be changing with the change of the delta, and essentially this is the line corresponds to no real power, no reactive power exchange. So, if it were operating this region, so it will be operating this region. So, as simple as that. Corresponding to the complementary voltage compensation line and the rated complementary QR versus PR line in the two region, including those are the purely reactive and the real power compensation can be fed. As it had been illustrated in the previous figure, the complementary voltage compensations lines are located symmetrically above and the below two reactive voltage compensation line, that is V1 P0 and V2 P0. Similarly, the corresponding complementary QR versus PR control lines are located symmetrically above and below the purely reactive compensation line in the circular control region of Q1R and the P1R plane. The complementary lines of the two systems must be opposite, upper versus lower, just it is complementary, halves of the relevant compensation of the control region. From the discussions, only one of the two systems, that mean in the prime system, it is possible to control both real and reactive power flow. On the other hand, only real power flow can be controlled within a defined line limits by available reactive power compensation, while prevailing reactive power line will be affecting by the real power demand of the primary system. And we have seen that actually the cord actually sinking as we were trying to actually supply more and more real power from one system to another system. Until now, the IPFC discussed for both power system angle for delta equal to 30 degree, and same discussion can be extended for another angle, let us say 60 degree, 45 degree or any other angle. Now, considering the system 1 with respect to variation of angle delta 1 moves to Q1 0 to P1 R 0. On a larger circular locus whose center is at PR1 0 and QR1 equal to 2 in the plane, let us see that what happened. And consequently, the center of the boundary of the circle Q1R versus P1R control region in the P1R and Q1R plane also moves along the circular arc with a varying delta 1, which we have actually we may find here. So, this is the varying delta. With decreasing the transmission line angle, the line current at a fixed compensated line impedance decreases. So, the length of that line becomes less. This means that the real power series connected converter with a fixed voltage rating can exchange with the uncompensated line decreases. For this reason, the range of the real power compensation decreases with decreasing delta unless simultaneous reactive power compensations has been put. So, we can say that simultaneous reactive power compensation to increase the line current of the transmitted power is carried out. So, this is basically some observation we can do for normal fax devices fitted with the IPFC. So, this is the case, you can see that this is a case delta equal to 0. So, this is your circle of influence, and where P12 equal to 0 in whole area, you cannot exchange any real power. Similarly, when you shift gradually, actually we are operating here. So, you can see that actually this line corresponds to reactive power compensation equal to 0, and this diameter corresponds to real power compensation equal to 0. So, this is the case which we have discussed actually for 60 degree. This is a case we have discussed throughout our discussion in the case of the 30 degree. In that way, you can see that this is basically the PR and QR, and so this is a line at 0.5 per unit. So, this is the line where actually P12 equal to 0 and whole controllable area. So, it is actually here, and thus actually gradually we can see that this bolt line actually gets shifted. So, for this reason, this is the relationship of UPQC IPFC with a change in delta. So, you can see that actually with increasing delta, it has a whole range of operations of the PQ. So, the control structure of IPFC is similar of the UPFC, which we have discussed before the IPFC, with the appropriate change of the control variables necessary constraint imposed by limiting the power transfer, because power transfer will take place between two lines. There in UPFC, it will be fed to the shunt path and it will be injected through the series path in maximum cases. A possible IPFC control will be shown into the next block diagram. For these structures, assumption of the previous sections stipulating the system 1 with IPFC converter 1, we will consider that is a prime and requiring the independent control both real and the reactive power. And subsequently, the logic of the second IPFC will be followed. The stipulation makes the control of the converter functionally somewhat different. We will see that. In practice, two converters control would be identical with the control input, putting one converter as prime and another converter will be on support. So, ultimately power demand, you will control basically P and Q of one particular line, and thus whatever P required to be fed, that will be fed from the other line. In that way, you are maintaining the power demand, real and reactive power demand by the one line, because since you are sending the real power, so ultimately you will be restricted by your actually demand of the supporting line. So, see that this is a control block diagram of the IPFC. So, this is actually Q1 ref and P1 ref, and this is I1 delta, and effectively actually this one is effective sending end voltage, that is V1 effective, and from there you will compute the in phase component of the voltage injection and the quadrature component of the voltage injection, that is essentially V1P star and the VQT star, and you will sense this value I1 and VQ1, and ultimately you will compare and you will be fed to the PI controller. This is essentially an error amplifier, and you require to maintain the DC bus voltage to meet the losses and exchange of the real power. So, VDC and the VDC ref, from there you will have an error amplifier, and what happened similarly for the, this is for the 1, and we assume that 1 is prime and 2 is supportive. Similarly, V2Q will be our some exchange of the power, and this is I and this will be IQ, and from there actually you will get the reactive power. Since it can inject, the second converter is independent to control the reactive power, so this logic will be same. But for the real power, it has its limited by the power handling capability of the real power, thus it will have a PQ limit, and that will be actually fed to this actually the sense inject voltage limiter. So, essentially it will be fed to the PI controller. You have a actually essentially it will be limit will be set by Vs1 and Is1, and thus it will actually generate the amount of the injections of the voltage required, and this will be the magnitude and the angle computing computer, and this will compute the amount of the V1 PQ required, and will sense actually I1. From there actually we will have a PLL loop. From PLL loop we will actually compute theta psi plus theta 1 essentially will be the effective phase shift given to the voltage P1Q, and that will be actually fed to the inverter, and inverter will actually inject that voltage. Similarly, we will have a I2 phase lock loop. From there actually theta 2 will be computed, and we will have an error amount of these things, and from there actually we will compute the amount of the PQ is required. So, it will be fed here. So, ultimately you will generate actually V2 PQ, and same voltage and the angle will be fed to the second converter. This is the way of operations of the this actually two interconnected IPFC. So, as shown in the control block, the converter 1 is synchronized to the line current I1, and converter 2 has to be synchronized with the line current I2 with two independent phase lock loop. We assume that there is no phase relation established between the two entities. It enables each converter provide the independent reactive power compensation to keep the operating voltage, operating conditions and the contingency to as a independent entities. The input of the prime control is either is desired the real and the reactive line power of P1 and Q1, or it could be desired in a quadrature of Vp1 or V1P. So, internal reference, that is V1Q, V1P from the P1 and PQ will be generated. The component of the V1Q being quadrature with the prevailing line current I1 represents the reactive compensation to control the transmitted real power. The component V1P star phase with that represents the series real power compensation to control the reactive power flow of the line. So, it will be just opposite to the, it is a cross relationship. Internally provided reference of V1Q and the V1P are compared with the actuals of V1P and the V1Q, and it is fitted to the PI controller, and thus we generate these two logics, and thus obtained an error signal after appropriate amplifications is possible, and we thus generate actually phi 1 and corresponding with the voltage of Vp1. Similarly, so limitation proceeding the computation of the V1 PQ and psi 1 is an important function of IPFC control to ensure the system operation within the predefined constant. The second set of constraints are unique to IPFC, are related to the possible limit of line 2 to carry the demand of the prime lines compensations. These limitations may result in insufficient current to line to supply the real power. to maintain its the DC bus voltage from the limitation imposed by the real power. So, this is something the unique features that has to be considered while designing the IPFC. The control of the converter 2 is different from the converter 1 because it must support the operation of the prime IPFC, and it has to fit the actually power demanded by the IPFC. Thus, its requirement means that since in phase component of the injected compensation voltage is imposed on the line 2 by real power demand line 1, the control of the converter 2 can influence only the transmitted real power. Its own line controlling the quadrature component of the V2Q of the injected voltage vector V2PQ. Thus, the reference input of the control of the converter 2 is desired quadrature compensating voltage of the V2Q ref. So, the reference voltage of V2Q ref is compared with the V2Q derived from the PI controller, and from this, from the amplitude of the error representing the difference between the desired and the actual bus voltage is computed. The magnitude of the VPQ with angle psi 2 is injected and second converter is operated. Thank you for your attention. We thus finished IPFC in details. We shall continue to our next class, that will be our concluding class. We shall take a case study in next class, and we shall see that in a particular area how different kind of fax devices and its synchronization operation can give you an appropriate power monitoring, control and stability operations. And we shall also discuss the advantage and disadvantage of different kind of fax devices and its basic philosophy. Thank you for your kind attention.